least squares regression coefficients. Okay, so how do you find the best fitting line? If you can draw, I mean, there are an uncountably infinite number of straight lines that I could draw through this data set, right? Which one is the very best one? Well, first of all, note that to describe a straight line, all you need are a slope and a y-intercept. So you need to find the slope and the y-intercept of the line that sort of best fits the data point pattern. Well, one way to do it is with this so-called sum of squared errors. By the way, this says let's see, what does this say here? The coefficients in the least squares regression take on values that minimize the cost function in some place. Okay, don't worry about that. But you can think of this sum of squared errors as a certain cost function that you're sort of trying to minimize. Okay, these squared errors. This is what we mean by squared errors. Okay, you have a data point pattern. Maybe it's we'll take some points that are positively associated. Maybe something like this. And the idea is, you can draw any old line through these data points. Maybe something like that. Here are my errors. Okay, this error is negative. This one is positive. This error is positive. Okay. This error is negative because it sits below the line. This error is small and negative, sits below the line. This error is negative because the point sits below the line. Okay? So it turns out if we just simply averaged, if we found the line that minimized the sum of the errors, it's not gonna do us any good. It's similar to the conundrum that you have when you try to calculate a variation measurement by just taking the average variation. You remember when we find standard deviation, we actually find underneath the square root sign, we actually find the average squared variation, or the average square deviation. So what we actually want to wind up doing here is squaring those errors. Gets rid of the minus signs. Right? And so when you square these errors, you're actually just finding the areas of these squares, right? And so that's exactly what you do. You want to find the line that minimizes this sum of squared errors. Squared errors are these areas of these squares. Okay? You can imagine that if I move this line far away, then I would get some really big squares. But if I can try to get this line really close in there somehow, the total areas of the squares gets to be small. So I can write this sum of squared errors like this. It's the sum of squared errors. Okay, I runs from 1 to n over the total number of data points. Now, what is an error? Well, it's the y coordinate of the ith value minus this guy. Okay, it's y hat. The hat values are the values on the line. Okay, so for example, if I have a data point right here, then if this is the ith data point, okay, then its coordinates are xi, yi. It's this height here, this value here, will be yi hat. You can think of it as the value that the line sort of predicts to be the response value for if the independent variable value is set to here. Okay, so the error is just this minus this, in which case that would be negative. Okay, so you sum up those squared errors, and by the way, so since these y hat values are really just the values on the line, we want this y hat. The line is going to take this form b naught plus b1x, right? So I can just substitute this in for the, if I put an I on there and an I on there, then if I substitute this in for y I hat, I get this. Okay. By the way, whenever we write a hat over something in statistics, it means that we're estimating the thing underneath it with the quantity there, with the with the hat on it. So, like for example, if this is Matt Jones, okay, then this is an estimate for Matt Jones. Okay, that's the idea. The hat sort of says estimator. All right, so what we'll want to do is we want to minimize this cost function, or minimize this sum of squared errors with respect to the slope and the y-intercept. We want to find the slope and the y-intercept values that make this sum smallest. Okay, it turns out you can show that in fact this is this function is concave upward in these two variables, b0 and b1. Okay, and so what we can do is differentiate it then with respect to b0 and with respect to b1, and set those two derivatives equal to 0. So you get this sort of parabola shape in those two variables, b0 and b1, and you want to find the where a function meets its minimum. You can just set the derivative equal to 0, provided that minimum is not on a boundary, of course. So doing so, now here I'm sort of skipping a step. Remember, this will be the derivative with respect to b0 of the sum. I goes from 1 to n of, now what's that, ei squared from the other page there? It's y sub I minus b1x I minus b0 quantity squared. Okay, so if I differentiate this stuff, I know how to do that. Turns out the derivative of the sum is the sum of the derivatives, so I can actually pull that derivative operation inside the summation there, and d b0, okay, of yi minus b1 xi minus b0 quantity squared. I know how to do that. I use the chain rule, right? I can, let's see, first of all, I pull the 2 down, right? And then this becomes a 1. And then I'll multiply by the derivative of the inside with respect to b0, which is just negative 1. And so that's exactly what I get. Negative 2. There's a 1 up here. Okay? All that stuff. And I set that derivative equal to 0. Okay, because I'm trying to minimize that. And so when I do that and carry it out, it turns out, after just a little bit of algebra, you should see that in fact b0 takes the form y bar minus b1 x bar. Okay, that is the y-intercept of this sort of best fitting line is the average y value minus the slope, whatever this number is, we don't know what it is yet, times the average x value. And actually, if you rearrange this looks a lot exactly like what y bar equals b1 x bar plus b0. Okay, so it turns out you can see already that that y bar x bar, or sorry, x bar y bar will actually sit right on the line. The line runs right through the point. X bar y bar. X bar y bar solves that equation. So that's kind of nice. That is, the best fitting line is going to run right through the so-called center of mass of the data point pattern. Okay, so to get an expression for B1 now, what we want to do is differentiate this sum of squared errors again, but this time with respect to B1. And this time it turns out to be this. And if I set this equal to 0, it turns out after a bunch of algebra you can in fact verify that B1 takes on this form, which is really pretty cool because look at it. It's super easy. It's R, the correlation coefficient, times the ratio of the standard deviations. Okay, this has a really nice interpretation. The slope for the original data set, for the regression line running through the original data set, is has a lot to do with R. That sort of makes sense, right? If R is positive, then there's a there's a positive association between the two variables, and the slope will go, the slope of the best fitting line will go this way. If R is negative, then the slope should go this way. So in fact, the slope of the regression line inherits its signage from the R value. Both of these standard deviations are always non-negative, right? So this fraction in here will be will be positive. And look at what that tells you. It says, it sort of indicates to me, I think, that if you have a data point pattern that's, maybe the R value is positive, but if it sort of tends to, if the variation in the x direction is a lot more compared to the variation in the y direction, then that indicates that sy over sx is going to be less than 1. And so the slope of this regression line will be something less than 1 times r. On the other hand, if you have a situation like this where the data point pattern seems to have a variation in the up-down direction that's more with respect to that of in the x direction, then the slope of the regression line will be, the standard deviation with respect to y is more than the standard deviation with respect to x, so this fraction here will be greater than 1, and you have something greater than 1 times r, and so you could actually get a slope that's greater than 1. Okay, so that's kind of nice there. Okay, so one more thing, and then we'll get back to doing some R. You could also multiply through that 2.2 there by n, and then also do it again by multiplying through by xi and summing over I to obtain these so-called normal equations. Okay, these will come in handy later on, especially if you ever take any experimental design coursage. These are easily solved to give an alternative but equivalent and useful expression for the slope. Okay, so sometimes we may want to think about the slope this way and look at what you have here. So the slope of the regression line, it's a ratio of sums. In the numerator, you have for the ith value, you have it's almost like a z-score, right? It's an absolute distance in the x direction times the absolute distance in the y direction, and you're summing those products. And in the bottom, you've got it's sort of like a variation measurement in the x direction. So it's sort of a mixed variation measurement in both variables in the top over the variation in the bottom. In the bottom is the sort of a variation measurement in the left-right direction. Okay, so let's take a look at this example. Open the data set called CH01PR19 from ALSM. ALSM is what we'll use to refer to our text, Applied Linear Statistical Models. Now this book will either come with a CD with a bunch of data on it, or you can just Google Applied Linear Statistical Models by Kuttner and Lee and so forth. You'll find a bunch of websites where you can get these data sets. So I've stored mine. I'll show you. Looks like this. Okay, Kuttner data. Okay, and I've got them all right here, organized by chapter. You probably find it at the publisher's site too, by the way. Go into chapter 1. Now, to open this in R, this is the file I want. By the way, you can click on it. It's a notepad file. Let's see. It's a text document, probably a .txt file. There, let's see. Yeah, .txt. But what I want to do is I want to open it in R. So to do that, you've got to set your path in R. So you got to set I guess you could set your working directory. So here's how I'm going to do that. I'm just going to click up here and copy the path, okay, to where I have that data file. And I'll go into R. And in fact, if I say get WD for get working directory, you'll see that this is my current working directory. C:\users Jones Matt / documents. Now, what I want to do is I want to set my working directory, and I'll do it this way. Okay, parentheses with quotes in there, and I'll Control V, just paste all that stuff that I just copied. Copied the path, and if I hit enter, I'll get an error message. Okay, here's one thing you have to be careful with R, is it doesn't like backslashes in the path. You're going to want to, by the way, here's another trick. If you use the up arrow like that, it'll get all the previous commands you typed in. So if you want to, use something you've already typed, I'm just going to go through this way and change these all to forward slashes. If I were smart, and I'm not, I would just put all this stuff into a folder on my desktop and have a short path name, because I'll be doing this pretty often, I guess. Alright, so now if I type get working directory like that, there you can see that now R is looking, my current working directory is actually where I want it to be, okay, in the chapter 1 data sets of the Kuttner data. So so now let's let me type this command, vars equals C GPA, comma ACT. And I'm going to do that because I happen to know that the two variables associated with that data set are GPA and ACT respectively. Okay, and now this way, when I now what I'm going to do is I'm going to read in the data. Okay. Use the read.table command. You can read this file. It's a text file. Okay, it doesn't have a header, but the column names will be those from this array called vars. Okay, is what I'll do, and I'm just going to call this this thing data. Okay, and if you want to see the first few lines of that data set, and just type data. Okay, or if I want to see the whole thing, I could type data and get all 120 rows. Okay, but oftentimes, sometimes it's good to take a quick summary, and you can see the first few rows of a data set, just kind of get an idea of what's going on and what the variable names are and so forth. Another useful command is you can type names and in your data set, and it'll tell you the names of the variables. Okay. But, all right, so what I want to do is I want to actually sort of go about doing regression the long way, using the formulas that are here in the notes. And I'm going to do that by computing slope, and I'm going to set slope equal to, by the way, you can use equal to, or you can use the, this symbol. Either way is fine. But it's going to be the correlation, right? That's this command, COR, gets the correlation. The correlation of the GPA variable with and the ACT variable. Okay, that's this. All of this stuff right here is our R, right? Times the ratio of the standard deviations, right? The standard deviation of the Y value divided by the standard deviation of the X value. See, the idea is maybe you want to use ACT score to predict GPA. All right, so I'll do that, and boop, it doesn't tell me what it is, but if I type slope, there we go. Slope is about 0.0388. So that indicates that, I mean, depending on how good the actual prediction is, that the data seem to sort of indicate a trend such that for every for every point increase in ACT score, you get about 0.0388 of a point increase in GPA. So what's the correlation there? The correlation is not very high. Okay, 0.26, 0.27 is not very low. So that, and it's not very high. It sort of indicates a pretty weak to moderate, maybe weak degree of association there. But we can also get the intercept. You can get the intercept for the best fitting least squares regression line by using that formula from the notes, right? It's the mean. It's the mean of the y values minus the slope, the b1, right, times the mean and the x values. Okay, and I can see exactly what that is. And so this means that when the x value is 0, it predicts a y value of 2.11. That is, for an ACT score of 0, it predicts a GPA of 2.11. Okay, that really kind of doesn't make any sense, but that's, you know, what our best fitting line is sort of predicting. Okay, so this means that the equation of our regression line would be would be this, right? 0.03882713 is our intercept times is our slope times ACT, our x variable, plus this is our y-intercept. Okay, and we put a hat over the GPA variable. Okay, because we're saying that you could estimate, potentially, you know, maybe estimate the GPA with this kind of a linear function of the ACT score. Okay, I can also let's type this, see what this does. Fit will be linear model. Okay, of the GPA variable versus the ACT variable, and now you know, if I just type fit now, then that'll give me the intercept and the slope. But if I do summary of the fit, I get a lot more stuff. Look at all this stuff. Okay, first of all, you see here are your intercept and slope coefficients. Okay, just as before, but you get a lot more stuff. Okay, first of all, there's something called a residual. The residual is just the error off the line. It's the errors off the line, and so we can do statistics on those residuals, and we'll talk about more about those coming up. The minimum, or the leftmost residual, is negative 2.74004, and the maximum of those is 1.22737. Again, these residuals are the actual observed errors off the line, positive and negative. Okay. Here again, these are our intercept and slope estimates. Turns out, and we'll talk about this in the next, I think it's the next week's worth of notes, that you can actually, you can do t-tests. You can do hypothesis tests to see if these intercept and slope values are significantly different from 0, or even significantly different from anything. And that's what these are, p-values over here. These are the associated test statistics, but these p-values are indicating that, yeah, in fact, these estimates are significantly different from 0. There is evidence in the data to suggest that the actual slope is non-zero, and that the actual intercept is non-zero. These are, you know, both certainly less than 1%. And the stars here sort of indicate, you know, here's the code here that tells you sort of what the stars mean. 3 stars means it's really, really significant, I guess, and 2 stars means that it's significant at the 1 in 1,000%, 1 in 1 divided 1 part in 1,000 level of significance, and so on. Okay. Got some other things down here. We'll talk about all of this stuff coming up. Turns out this multiple r squared, this is just the same as r, or the correlation coefficient, squared. Okay, whatever that means. It's also called the coefficient of determination. We'll talk about that. We'll talk about this a lot. Actually, this will play a big role in this course. The residual standard error. This is the standard error of our residuals. Okay. Or those errors off the line. This is adjusted r squared. This is, well, it's related to this. Again, we'll talk about this, and we'll talk about all these things. The summary command here is what gets all of this for us. It gives you a lot more information. Next up, we'll talk about the regression model.